6.5 is about solving exponential equations. This is going to be a short lesson, but it gets kind of hard towards the end. Basically, what this means is we're going to have equations that have exponents in them. And if both sides of the equation have the same base, then they must have the same exponent. Let me write an equation out, and hopefully that makes this obvious. So the example here is, if I have an equation 2 to the x power equals 2 to the 5th power, well, what's the only exponent that's going to make this equation true? It's got to match. The only thing that's the same as doing 2 times 2 times 2 times 2 times 2 is also doing 2 times 2 times 2 times 2 times 2. It's the only way you're going to get these equations to work out, and it just kind of makes sense. So typically what we would do is write an equation between the exponents and forget about the bases. The bases already match. Now we just need to make sure the exponents match. So this is just x equals 5. There's not much to do for this problem. Here's 3 more examples of solving equations like this. So again, if the bases match, the exponents have to match. So my method for solving this is write an equation between just the exponents. I already know the bases match. Now I need to make sure the exponents match. So I'm going to subtract 1 on each side, and I get x equals 4. That's my solution to the equation. How about this second one? Well, the left side doesn't look like it has an exponent, but it does. The exponent that doesn't do anything, so it doesn't need to show up, is 1. I have 6 one time. Well, that's just 6. So if you don't see an exponent, there's going to be a 1 there. So same thing. Write an equation using the exponents. I'm going to add 3 on both sides. And then finally divide by 2 to get x alone. 2 equals x. So if I plug that back in up here, 2 times 2 is 4. 4 minus 3 is 1. They would both be 6 to the 1st power. Finally, the 10s match. So I need to write an equation with the exponents once again. Now I got x's on both sides, so let's just remember our equation solving strategies. Get all the x's together, so I'm going to do minus x on both sides. So I'm just left with 1x equals 3. That's just x equals 3. So 3 times 3 is 9. 2 times 3 is 6, plus 3 is also 9. Okay, so this is finding the x values that make the exponents match. Our next problems are going to be a little bit trickier because the bases aren't going to match, but we'll figure out how to handle that. So this is an example where the bases don't match. This one's a 5, this one's 125. Okay, so what we want to do here is, the only way this is really going to work is if one of these is just a multiplied up version of the other. All right, so one way we can figure this out is divide by 5 until we're left with only 5s, kind of like a factor tree. 125 is 5 cubed. How many 5s do I need to make 125? So this equation is the same as 5 to the x power equals 5 cubed. So now I can do what we did on the first couple problems. Now that I got the bases to match, I want to write an equation with the exponents. Okay, so this is called changing base, because you're literally using your exponent properties to change the base number. These are the same. 125 and 5 cubed are the same number. It's just 5 cubed is what lets us solve the equation. So same thing over here. 4 to the x power equals 2 to the x minus 3. Okay, the 4 needs to do the change of base thing. So what I'm going to do is I'm going to put the 4 in parentheses, and then when I'm done with my change of base, so this is 2 squared, this is what shows us that we would multiply the results together. All right, if you remember our power of a power property, 2 squared, then to the x power, I would multiply these and get 2 to the 2x equals 2 to the x minus 3. Okay, so this goes back to 6.1 a little bit. Power of a power is what tells us what to do after I've done my change of base. Okay, you didn't see it over here, but this was 125 to the first power. Then it would have been 5 cubed to the first power, but 3 times 1 is still just 3. Over here, we actually have to multiply. It matters over here. All right, so once again, now we're set up to do what we did on the front page. Just write an equation between the exponents. Subtract x on both sides to get all the x's together. I get x equals -3. Finally, one more. We've got 9x plus 2 equals 27 to the x. Now, this one's even a little trickier, and your number sense, I'm going to erase this problem just to give myself some space. Your number sense has to be a little bit on point for this, because you need to know that 9 isn't going to go straight into 27. This is an example where we have to find a different base for both. In this case, 9 is a perfect square of 3. 27 has 3 3s as its factors. So I'd get 3 squared, and then the x plus 2 that we saw over here. And this one would be 3 cubed, and then the x that was up here. And now I'd multiply. Power of a power again. So this comes out to 3 to the 2x plus 4. When I multiply those, I have to distribute, because 2 is multiplied by the whole x plus 2 expression. And then 3 to the 3x. It's not a ton of work, but it's going to take a little bit of practice. So it's nice that the notes are so short so we can just do a bunch of these. All right, now I would write my equation out again. 2x plus 4 equals 3x from my exponents. Subtract 2x on each side to get all the x's together. 4 equals 1x, or just 4 equals x. So when we change bases, doing this factor tree helps us out. Having a little bit of number sense matters for these problems, where I'm going to have to find a completely different base for both numbers. Now we got even a little more of a sticky situation. 1 over 2. All right. What the heck am I going to do with that? It's really not too bad. We just have to remember our negative exponent property. Negative exponent property. Now, normally we flip something to get a negative exponent away. But now I want the 2 on top. I want this up here. So to do that, I've got to make its exponent negative. 1 over 2 is the same as 2 to the negative first power. I write that a little bit better. 2 to the negative first power. Okay, what I have written here is the same. 2 to the negative first power, normally when we simplify that, we would put it down in the denominator. Now we're going backwards because it helps us for our algebra steps. Okay, now I've got a base of 2. That's something I can work with for the 4. So I'm going to have 2 to the negative 1x equals 2 squared. And now it's just as simple as what we were doing before. Negative x equals 2 from the exponents. divide by -1, I get x equals -2. Okay? Change of base definitely isn't the prettiest math we've ever done. It's working with fractions and negative exponents. So sorry if you struggle a little bit, but again, it just takes practice. This isn't a particularly long problem. We just have to do some weird math. Let's do one more. Last example problem on the notes is 4x plus 1 equals 1 over 64. All right, now I'm going to handle this the same way I handled my 1/2. I'm going to move the 64 up by giving it a negative exponent, 64 to the -1. All right, now we run into a change of base problem. 64 breaks down into 4 and 16. 16 breaks into 4 and 4. So 64 can be written as 4 cubed. So I'm going to try and show my math this time in a way that hopefully makes sense. So that -1 we made earlier, the -1 exponent, is still there. And then when we do our change of base into 4s, now it's 4 cubed. So it needs to be 4 to the -3. I have to multiply these with power of a power again. So I'm going to get 4 to the x plus 1 equals 4 to the -3. And now we're back to just as easy as the front page. Just took a little bit of work to get here. Bases match, so I want to make the exponents match. Have to subtract 1 on each side. I get x equals -4. All right, we'll spend a bunch more time practicing these together, but it'll make you work with fractions and negative exponents in a way we haven't done before. So hopefully that makes you understand and remember our properties a little bit better.